Hello students, and welcome back to our discussion of Chapter 8, Hypothesis Testing. We've done an hypothesis test for the average when the population standard deviation was known. That was the example with McDonald's. We've done an hypothesis test for the average when the population standard deviation was not known, and that was the city of Red Deer average income example. Now we'll be doing another type of an hypothesis test. This is a test on the population proportion, proportion meaning percentage or fraction of the population that exhibits some characteristic. Same process, except for the standard error of the proportion formula, which is part of your Z formula. So let's just go into that. This is back from similar to Chapter 7 with slight difference. The standard error of the proportion is going to equal the population proportion times 1 minus the population proportion over the square root of n. So that is what we need to calculate as a standard error. We can do that before we calculate Z, or we can do that as part of the Z formula. So let's go into an example. This is an example on page 103. At least I hope it's on page 103. This one states that it is assumed that at least 65% of all registered voters will vote for candidate A on the next election. In a sample of 500, it was determined that 60% would vote for candidate A. Are the election polls wrong in saying that at least 65% of all registered voters will vote for candidate A? We're testing this claim at 5%. Let's go into this example here. Let's find, we're doing the same process. So step 1 is to determine the null hypotheses. This question does not have anything about the average or standard deviation, and it's talking about a percentage or proportion of a population. So that's why we know that it is a proportion. 65%, it says at least. So this is that symbol. At least 65%. We're going to keep it as a decimal. So this is step 1. Step 2 is to determine the alternate hypotheses. This question does not have both statements clearly stated in here, but we know that the null hypothesis is at least 65%. The alternate hypothesis is always opposite. So if you go back to the PowerPoint slides about the different formats, we'll know that if the question states at least 65%, greater than equal to, we know that the opposite sign is just less than 65% in this case. One thing to remember, that the equality part, it's equal or greater than equal to or less than equal to, that equal part is always part of the null hypotheses. So step 3 is determining if this is a one-tailed test or two-tailed test. This is a one-tailed test because of the inequality. Greater than, less than signs are one-tailed test. We're going to find a critical value, so that's the key word. Find the critical value. Proportion test is always based on a Z value. So remember, or in this case, alpha, just to write this down, is 5%. And remember, we can always find our critical values on the t-distribution table, which is right here. Let's bring that down. It up a little bit. There. Let's write this over here in black. I should have erased that, but so this is the hypothesis test. Alpha is 5%, and it's a one-tailed test. So we don't divide alpha by 2 in this case, we just leave it. So 5% right in here, this column. it's a Z value, so we know the Z value 1.64. We're not concerned about degrees of freedom. So critical value for Z 1.64. So Z has a critical value of 1.64. Technically, it's going to be negative. A couple ways to determine that. The direction of the alternate sign is it's pointing towards the left. The left is negative. Also, we can tell because the population value is 65% and the sample proportion is less than that at 60%. So 0.6. So if the sample proportion is less than the population value, we know we're working on that left end. So this would be akin to saying that, in the proportion that's assumed to be true, we'll just keep that there, 0.65. It is a one-tailed test. Any value that's less than this threshold value, which is denoted as a Z alpha value, negative 1.64, this is our rejection region. We only have one of them because it's a one-tail test. So we've done the first 4 steps. We can go into step 5, which is calculating the test statistic, which is sample proportion minus the population proportion over the standard error. And we're just going to write this in here. So 0.6 minus 0.65 divided by 0.65. 1 minus 0.65 is 0.35, and a sample of 500. So this math would show us that the Z value is negative 2.34. Negative 2.34 is going to be way over here. There's negative 2.34. Clearly within this rejection region here. This would just keep on going on forever. So step 6 is to make our decision. We are going to reject the null hypotheses if the test statistic is greater than the critical value. Keep in mind that when we make our decision, we turn both values to, positive. So we are going to reject the null hypotheses if 2.34 is greater than 1.64. So therefore, we are clearly going to reject the null hypotheses, which basically means gives us permission to cross this out, and we are left with the statement that it's less than 65% of the people that would that are indicating that they would vote for candidate A. So before we go on to the next section, I'm going to change this question up a little bit. Let's work on this sheet here. Let's bring in that question again. So this is an adjusted question. It's not part of the PowerPoint, and it's not specifically part of in the course package in terms of using this question. We're going to change this question right here. The sample is 100. So basically n equals 100. Maybe the poll company only had enough time or money to survey 100 registered voters. Let's see what kind of difference that would be. Okay, we know that the null hypothesis is the same, at least 65%. We're testing the opposite, that it's less than 65%. We know that's one-tail test. It's a critical, finding the critical value. It's a Z value. Critical value doesn't change. It's still negative 1.64 because Z is not based on sample size. Step 5, let's number these again here. 1, 2, 3, 4. Step 5 is to calculate the test statistic, which is once again based on this formula. Let's make that obvious. So the only difference in this question is their sample size. .65, 0.35 divided by 100. So that's the only difference we've made right here. Everything else is the same except for whatever reason we only surveyed 100 people. What kind of difference is that going to make in our decision about the null hypotheses? When we carry out this calculation, we'll find that the test statistic, let's run that number. Test statistic equals negative 1.05. We'll round that up a little bit. So remember, our decision is to reject the null hypotheses if the test statistic is greater than the critical value, assuming that we just changed the Z values to be positive. So we're going to reject the null hypotheses if 1.05 is greater than 1.64. It's not, so we cannot reject the null hypotheses. So our decision here is that we have failed to reject the null hypotheses. We're going to write the opposite statement: do not reject the null hypotheses. This means that we can't cross this statement out. We're not going to say that it's true. And that's the reason I did this secondary adjusted question. Our only correct decision is do not reject the null hypotheses. We're going to leave it up to candidate A or his team to determine if he wants to publicly declare that, hey, this statement is correct, at least 65% of the people will vote for me. The problem is our sample size is quite small. It's only 100. What happens if our sample size grew? If we now had a sample size of 500? Well, you should remember that when the sample size was 500, our decision was to reject the null hypotheses. So that's back on that original question. So the difference, now that the sample size was only 100, we are left with the conclusion not to reject the null hypotheses. We do not want to say that the null hypothesis is good. We do not want to say this: accept it, the null hypothesis, or HO is good. And let me just emphasize that we will not say that. We will not say that because if we had a better sample, our decision could change to basically saying that the null hypothesis here is actually bad. So we don't want to make that decision and be wrong. That's why we will say do not reject the null hypotheses instead of saying that the null hypothesis is good. Because if we had more time and more money, we'd have a bigger sample size and our decision could change. We'll cover more of that in the next video.